Okay, we're back. This is video 2 of the equilibrium video introduction. So let's practice writing those equilibrium expressions for using the law of mass action. So in this equation here, we're going to put the products over the reactants. No coefficient, so there won't be any superscript. For letter B, we'll do our products, SO3. We're squaring that because of that 2. Squaring that because of that 2, not that 2. And for C, we've got S2. We'll use that 4. S8. That's kind of ugly. And we're using these square brackets to represent molar concentration, moles per liter. And we can only use, the only thing we include in the equilibrium constant expression are things that can be measured in moles per liter. The rate constant K was usually written with units, like moles per liter to the -1, second -1. The equilibrium constant K is usually written without units. That's just by convention. There's no real reason not to, other than they just can get kind of cumbersome, and there's not really much to gain by using those units. If you want to know what they were from those previous problems, on A and B it was moles per liter to the -1, and for C it'd be moles per liter cubed, and I believe you can see that here, moles per liter squared, right, because both of those were moles per liter. You're going to cancel one of those. To the 4th. Or moles per liter to the 1st, so it would be moles per liter cubed. They might ask for that on the AP exam. It won't be every time if they do. And the only thing, the only thing we are including are things with concentrations, things that can be measured in terms of moles per liter. So only solutions and gases, aqueous solutions and gases, no solids or liquids. And so far, all of the ones that we did, those A, B, and C, were all homogeneous equilibrium. Everything was a gas, everything was a liquid, or everything was either a gas or an AQ. I believe they were all gases. Sometimes they're not that way. Sometimes you'll have multiple different states of matter, like on this letter A. We've got some solids, and we got a gas, so we're only going to include the gas. Your best bet would be to throw in a number 1 wherever there's a solid or a liquid. So the products here, P4O10 is a solid, so I'm going to put a 1 on top. P4 is a solid, so I'm putting a 1 on the bottom. And then my O2 is a gas, so I'll put that. And you could just say 1 over O2 to the 5th, because we're not including solids in our expression. We can't just leave it blank on top because it has to be in the denominator, the O2. There's one with, that first one, that looks like a gas, but that's a solid. All right, so it'll be N2O concentration over 1. You wouldn't have to put the 1. Here we got a gas, a solid, and a solid, so it'll be 1 over CO2 concentration. There's another 1 down there if you want it. And finally, we've got solid, 2 gases, SO2 to the 8th, O2 to the 8th. And even though you might be tempted to, you cannot cancel those 8s. I don't need can't. I believe we've talked about this symbol before. An equal sign with 3 lines means they are identically equal to each other. So when we use just a K, we actually mean K for concentration units. So Kc, sometimes you'll see a Kc, generally just K. We could write the equilibrium expression based on the partial pressures of the gases, in which case, instead of using the square brackets for concentration, moles per liter, we use just regular parentheses for that, and we use the capital P for the pressures. So if we went back to those first 3 examples on page 7 of this packet, which you don't have a copy of, and we wanted to make them KPs, we will just change the concentrations into pressures. So instead of what's written there for A, we would have P and for letter B, and for C, and at a later time we will learn how to convert between Kc and Kp. But for now, let's pretend we don't have to worry about that. And just another note for future reference, we will see a lot of different Ks, Kc, Kp, Kw, Ka, and so on. And there may be others. And the good news is they all work the same way. So you only have to learn how to do it once, that's what we're doing now. The why we want to do it will be specific to each one. So right now the why is we're doing for concentration or for pressure, writing an equilibrium constant expression. It's going to get more mathy. Just saying. All right, so let's do a little calculation. We're calculating K from either concentration or pressures. So here's an example. Considering the following reaction at a certain temperature. The reason we include the temperature is because the only thing that affects K, the only thing that changes the value of K is changing the temperature. The only thing is changing the temperature. So they'll generally put a temperature in the problem. So we've got this equation, the 4 irons plus 3 O2 gas, making 2 Fe2O3 iron oxide, which is essentially rust. This is iron. This is rust. So we're making rust. Both the iron and the rust are solids. We're not going to include those in the expressions. They're giving us an amount. We're not going to run out of either one. And we're in a 2-liter container. So in order to make this work, we're going to have to calculate a concentration for the O2. And it's 0.001 moles divided by 2.0 liters, which is 0.0005 moles per liter. Here's my expression for K. I'm going to plug in for the O2. And I think I'm going to get a pretty crazy number. It's 1 over 1.25 times 10 to the minus 10, which is 8 times 10 to the 9th. What would the units be in this case? Moles per liter to the -3, if you care. I don't care. You probably don't need to know. You'll probably never be asked to calculate it. And here's one using pressures. The pressure of the H2O gas is 15 torr, and the total pressure is 36.3 torr for the entire container. We don't know the value of Kp. We're going to have to do a calculation. We know that this is 15 torr. We don't know what this pressure is, but we know the total, so we can use the total and subtract off what we do know, the 15, and then it'll give us the, what is that, 21. Yeah, 21.3. So our Kp expression in this case will be pressure of H2 to the fourth over the pressure of H2O to the fourth, which will be 21.3 torr to the fourth over 15 to the fourth. Wow, that's going to be... I'm getting 4.06. Let me punch that in one more time just to be safe. Hmm. 4.065, 4.07. So that's an example of both kinds of problems. Let's see what we got here. Oh, it's the last page. Even though the rate forward and the rate reverse are the same, we usually don't know what they are and probably don't need to know. And since the value of K is calculated from the number of or the amounts of products over reactants, if the reaction favors products, that means you have more products than reactants, then the value of this fraction becomes greater than 1. And I tried to show that graphically with the different size font. And if the reaction favors reactants, that means the reaction doesn't go forward hardly at all. Then your K is going to be much less than 1. So you have very little product and a lot of reactant. And the value of the equation, or the value of the ratio, is very small. So that concludes what I wanted to give you for today. Hopefully I can get this uploaded to YouTube, and you can watch those during class. Thank you very much. See you on Monday.